Welcome in. All right, so let's extend the one dimension momentum to two dimensions. So in one dimension, here is our formula. Well, our formula is going to be the same, except we're going to be breaking it down in terms of its components. So what is the only difference in two dimensions in comparison to one dimension? Well, first of all the conservation laws that you have, so the momentum conservation or kinetic energy conservation, if it's for the elastic cases, all of these things still hold in two dimensions. So they just simply extend from 1D to 2D. Now, for anyone who has worked in two dimensions or even three dimensions, then they know they're going to have to be dealing with vectors. But if you're doing physics, that shouldn't be new to you. Of course, vectors are going to be arising all over the place. And in fact, if you look at the definition of momentum, its original definition, it is a vector. So a vector, which is just simply mass multiplied by the velocity of the object. And it doesn't have to be going in a one-dimensional way. It can be going anywhere does it please. So our idea in the conservation happens both in elastic and inelastic for momentum. Now, if you are breaking this down in two dimensions and in collisions in two dimensions, then the momentum and the conservation is going to happen separately, both in the x and the y directions. So now you're not going to have just one-dimensional conservation, which is this case. You're going to have, and you're going to see this formula in two cases, which is going to be in the x and in the y. If you were extending it in three dimensions, it would have been a little bit more annoying, but you would have also had the conservation law of momentum conserved in three dimensions, except you would be dealing with x, y, and in the z direction or in the z direction. Now, in terms of kinetic energy, so here I'm going to just say briefly what we're referring to. So kinetic energy is conserved only in elastic collisions. Of course, we know that. Now, this, of course, happens also in two dimensions. So the only thing that you should be careful with kinetic energy when you're doing your calculations before a collision and after a collision, and then checking. Now, you can do it if it's elastic or inelastic. Just if it's elastic, then you're going to have the kinetic energy, which is going to be fully conserved into before and after. Now, if it's inelastic, it doesn't matter. The calculation of kinetic energy is still going to be the same. And that calculation, the way that you proceed is because now you are dealing with vectors, you're going to be taking and breaking down the velocity and taking its magnitude. So, for example, we know that kinetic energy is 1/2 mass, okay, times velocity squared. And that velocity, now the question arises, well, what is that velocity? Because I have a vector. Well, that velocity, you're going to have to take the magnitude of that velocity and then substitute it in. And of course, if they're going in various directions, okay, you're going to need to calculate both for the first object and the second object. And then after the collision, you're going to do the same exact thing. So you obviously can't substitute a vector into the kinetic energy. You need to substitute a scalar, and that scalar will just be the magnitude of the actual velocity. All right, so just keep that in mind right here. Now, in terms of impulse, well, impulse is defined in this following way. So it is the change of momentum that we have. And again, it can be broken down into its x and y components. So that, again, does not really change. It's just a matter of knowing how to break these things down. Now, what's the strategy here? Well, the strategy is rather simple. So you're going to be breaking things down in terms of its momentum and possibly velocities, for instance, into its x and its y components. All right, so that's the first thing that you would do. And then you're going to be applying the conservation of momentum separately in each of the directions, in the x and in the y. So here are the formulas that we have, and these formulas are nothing else but the one-dimensional formula, except we've broken it down into its x component and y component. So that's what we would have there. And then you can just simply solve. So you can solve there. You have two equations, sometimes two unknowns, or sometimes it would be two equations, maybe just one unknown, but you would be using it down. Now, in terms of breaking down into its components and using two dimensions, of course, you're going to be exposed now to trigonometry. So you should be comfortable with your sines, your cosines, your tangents, all right, with the Pythagorean theorem, so in terms of finding magnitudes in general. So all of that trigonometry still is going to play a role. Now, what do we mean by breaking down momentum, or at least its velocity, into its x and y components when we're doing these calculations? Like, how is this thing going to come about? So here it is. Okay, so this is at least a pictorial view. We just want to be able to show you, how we can break this thing down. So for instance, it will depend on how the vectors are, of course, given to us. Maybe they're given in XY components already. Maybe they're given not in XY components, okay? So, maybe we have the magnitude, maybe we have some angle. So we have to be seeing, what information is provided to us. But what we are referring to is that these are in 2 dimensions in terms of the vectors, right? So here is for mass number 1, and then here is for mass number 2. Now, I'm going to assume that this left-hand side is before the collision, and then here, the right-hand side is going to be after the collision. So hence you see initial, and then you see final over here. And here are the equations in terms of breaking this down. So the masses, well, they don't really change. So mass 1, mass 2, that's going to be the same one before and after. And notice this is the x component. So what do we mean here by the x components? Well, so if you would be breaking this down, and if we would assume, okay, so for the sake of, okay, here, where this is your x and your y, all right, if this is your x direction and your y direction, so I'm going to assume that. Now, if I take these, I can break these things down. So this would be my y component, and then this would be my x component, all right? So these are the 2 that I have, and this is exactly what you see right here. So this v1xi, well, that would be this component right here. So that's that component. And then if you're talking about the y direction, well, here, this would be the y direction, and that y direction would have been this component. Now, it will depend on what angle is given. I don't know if this angle is given, or maybe this angle is given, okay, or something else. So I don't want to be kind of leading you in that direction, because it will honestly depend. And this is where your trigonometry comes in. So, if, for instance, if this angle is given, then, if you want to find this component of this particular angle, then that would have been the cos, okay, of this one. If, let's say this angle is given, then that's different, right? So that would have been a different case. In that case, it would have been the sine. So you have to be careful on which angles are given, and then you have to be comfortable with, opposite, adjacent, hypotenuse. So all of that trigonometry stuff, okay, is going to come into play in these vectors. Now, if you're talking about your second mass, again, it can be broken down into its pieces. So here would have been your x, and then here would have been your y. And then again, so if you're looking at this, this would have been for your second mass. So here's your x component right there, and then here would have been your y component. And again, it will depend on which angle is given. I don't know which angle that would be. So, let's say if this angle was given, right here, I'll put theta number 2. Then if you want the x component, it would have been cos of that angle. If you want the y component, it would have been a sine of that angle. But again, it just depends on what is provided to us. Now, if you look on the final side, the same thing. So here, when we're talking about breaking down into its components, you're going to be breaking this down into its components. So let's say, after the collision, you're going to have an x component and you're going to have a y component. And then the same thing will happen to your second mass. So you're going to have an x component and you're going to have a y component. And depending on, again, what the angles that are given, we can obtain these. So that's what we mean that the law of conservation is conserved, but it is conserved component-wise, okay? So component-based. So let's take a look maybe at an example so that we can see it, break it down. I'm going to, use this particular equation to substitute everything in so that you can kind of get a gauge on, how this will be. And hopefully, it's not that bad. It's just a little tedious in terms of its calculations. Okay, so let's jump into an example. So here it is. So here's the example that we want to do. It's not super crazy complicated. I am going to do some more complicated examples when I do kind of the unit test, okay, for this. Yeah, so this is the last topic, okay, of these momentum, and then I will do a unit test and then try to knock off, at least a question for each of the topics that I covered. But here's an introductory example of 2D collisions, okay, so let's take a look and then see what happens. So we have a small crate with a mass of 0.25 kilograms, and it's sliding across a frictionless floor at 15 meters per second to the left, all right, so that's the first one. So in this case, all right, so here's my before. I know it's a crate, I'll still use a circle in here. So it's sliding to the left, so it's moving in this direction right there. And it has a mass, so 0.25 kilograms. and it has, so that's check mark, and then it has a certain speed. Now be careful because it's to the left, so it depends on how you're going to be drawing this out. I'm going to assume that left is, negative, especially with regards to your x and your y. So here's your kind of standard axes. All right, if this is my x and my y, so I'm going to assume, positives and are to the right and up, and negatives are down and to the left. So here I would have been writing this down as negative 15 meters per second, or I can write it as 15 meters per second left. Okay, so that's up to us. Now, at the same time, it looks like it collides with a second crate of mass 0.45, so a little bit bigger, and that is moving downwards at 25 meters per second. All right, so it collides in. I'm just gonna kind of draw these side by side in here. It doesn't matter. So here, here we go. There's some collision. Okay, that happens. And this thing is going downwards. So that's the information that they're providing us. It's a little bit bigger, so 0.5 kilograms right there. And it is down. So again, I'm going to put negative 25 meters per second because of the down direction. So what are, these particular values, right? And then what exactly, do we have to solve in here? So it says that during that collision, they stick together. So that means it's going to be inelastic. So if you still remember that, okay, so if they do stick together, it's perfectly inelastic. And we want to determine what the speed is and the direction of their combined motion right after the impact. Now, again, please remember momentum is conserved. So I have to be writing all of these things in here. So here are my equations. And what I'm going to do is I'm going to try to break all of these things down. Now notice it's to the left and down. So I technically don't really need trigonometry, at least as of yet, because I only have x and y components. So for instance, I'm going to break this down one by one. So with regards to mass number 1, I'm going to do this and then do that. So that's my mass number 1. I know what these are. So for instance, the mass number 1, so this is going to be 0.25. Notice that's in metric standard units. And then the speed or the velocity is negative 15 meters per second. I'm dropping the units in here. So I know that that is the case. Now, with regards to the y component, it has no y component. So this is 0.25, and our speed in the y component is 0. So check mark, that's my x and my y. Now, if I look at my second one, so my second object, that would be this right here, and this right here. So if I wanted to do that, now I'm going to put here plus, all right, so right there, and then I'm going to put here plus as well. So in my x component, for my mass number 2, there is no x component. It certainly has a mass, but it has no speed at all in that x component because everything is in the y direction. So that's first component right there, and then 0.45. And this would have been negative 25 down here. So that's my left-hand side, both from my x and then from my y. And now, if I want to be able to solve, so now I have to look over what's happening on my right-hand side, right? So, what is all of these things right there? So I'm going to shift this just so that I have some space here. So let me shift this out of the way. Let me shift this out of the way right there. And then I'm going to write out, so this is my equal sign and my equal sign. So I have my x and my y. So this is my x component, this is my y component, right there, just so that you can easily see them. So they stick together. Well, what does that mean? So, well, if you remember from one dimensions, if they stick together, then they only have one full mass, right? There's no longer necessarily two objects. So within here, so what will happen is if they stick together, that means M1 plus M2 are going to be combined. And if you do that, so this is 0.25 plus 0.45, so I guess it's 0.7. All right, so that is the mass. And then on the y directions, of course, the mass doesn't change, so that's going to be still the same thing. And now, in terms of its speed, I don't know what the speed is, right? This is something that I have to find. So this is going to be v, and I'm not going to call it v1 or v2. I'm just going to call it v because they're stuck together. So it's the overall speed that they have, but it is in the x direction, and this would have been the final speed. And then on the y direction, it's going to be v, and then in the y direction, and then the final speed. So sorry, those are my f's. So there you go. You know, I have two equations. I really have two unknowns. So now I can just go ahead and try to solve for these. So, and what I'm going to be doing is I'm going to be solving for this right here and for this right here. So these are not very difficult. I can just shift things around and then solve. So let me do that in fast forward fashion, and then let's come back and see what they will be. All right, so there you go. Okay, so those are just the calculations that we would have. They're not very difficult in this particular case, which is great, but they are component wise. So if I wanted to be able to see exactly what this is, so I have the x and the y components. Now it doesn't actually tell us in what format they want it in, but I'll try to put it in the magnitude and angle format in here. So what we have is, here's my x component. So that component is moving to the x, and it's going to be negative 5.357. Sorry, I didn't round this. So we have that, and then we have our y component. So this one's much bigger. I'm not going to make it too huge, but okay, this is negative 16, 0.714. So this one's down. Okay, so the negatives and that I have, it just means to the left and then downwards. So you can certainly remove them if you wanted to. And now your resultant vector, well, the resultant vector, okay, is the vector that we would have right here. And then we would need to do, basically just use the Pythagorean theorem. So in order to find the Pythagorean theorem, well, what we're going to find out, so if we want to know what the magnitude of this is, okay, of this final v, I'll just call it v in there. So that magnitude is going to be equal to, so this is, again, so from trigonometry, well, not really from trigonometry, this is kind of still your Pythagorean theorem, okay, squared plus, and sorry, I'm not able to fit this in here, but I'll write it just below, and then we're going to square that as well. So, and that's going to give us what the magnitude is overall. And then if you want to know what the angle is, well, in order to find the angle, so again, this will depend on what you want. So you have to kind of be careful here, and depends on what your teachers want. So here, I'm going to draw an axis in here, right? So if this is the axis overall, kind of like this, then, if you're looking for this entire angle, okay, so if you want this angle all the way through, so you can certainly find that. Now remember, the top part is 180 degrees, and then we can certainly find this angle and then add it up, right? So this would have been, in order to find that angle, that would have been the 10. Now it's an inverse. And then again, remember, opposite over adjacent. So in this case, the opposite of that angle, okay, so that would have been this 16. So that is this part, okay, right? So this component right here. So that is your opposite, and then your adjacent is 5.357. So that's what we're going to be substituting in here. So that's your opposite, okay, and then this right here is your adjacent, okay, all the way over here. So I'm going to do that in fast forward fashion. I'm going to calculate this, and then I'm going to try to find out what that angle is, and we'll add it to 180 in case we want it with respect to the positive axes. Okay, so we'll be right back. All right, so we're back. Okay, so I just calculated it in. So here's our magnitude. I just rounded to two significant figures. And then here's our angle. And again, I just rounded it off. And so here it is in terms of the overall. So this is what would have happened when the two objects would have gotten stuck together. So, here's have been our final answers, which is 17 meters per second at an angle of 252, okay, if you're doing it with respect to the positive zero axis, okay, going all the way around, or just simply at 72, okay, below that y-axis on the left-hand side. And that is it, right? So in terms of trying to compute momentum conservations, velocities, okay, so this is what you would have been doing in terms of your overall items. Now, just as a final note, although it doesn't ask us in this question, for kinetic energy, so let's say if they were talking about kinetic energy, now we know this is inelastic because they get stuck together. However, if somebody asks you, is this an elastic or inelastic, and then show it by calculations, then you can certainly show it by calculating the kinetic energy. And what you would do is, so before the collision, you would have had two values, right? So here's my speed here, and then here's my other speed. So you can now find what the kinetic energy is beforehand. And don't forget, this is 1/2 m1 multiplied by v1 squared plus your 1/2 m2 multiplied by v2 squared. And you are taking the magnitudes over here. All right, so that's what you would have been taking. And then after the collision, so if you wanted to do after the collision, then, okay, so here, now we've already have it calculated, but this is after, or the final kinetic energy. This would have been 1/2. Now, keep in mind, this is now m1 plus m2. And then our speed, so specifically, we want the magnitude. So we are going to be interested in this value right there. So you would have been calculating it, and I'm going to put magnitude of your final, okay, speed squared. Okay, will have nothing to do with the actual angle, okay, as long as you have what the total magnitude is. And now this would be your afterwards kinetic energy. This would be your before kinetic energy. Okay, so you have to add these two together, and then you can compare, is it elastic and inelastic, etc. All right, so I thought to just add that in. All right, so there it is. Okay, it's kind of the last topic on this momentum streak for this chapter. I'll do a unit test for you guys, and then that's going to be the final kind of video with regards to all of the physics that I had to do. Okay, so I went back to do these momentum videos for you. All right, thanks for watching. We'll see you in a future video. Okay, cheers everybody. Bye-bye.